if I told you that the solar system doesn't end at Pluto, and that we may have missed a massive portion of mass right in our own backyard? Would you believe it? For decades, textbooks taught that beyond Pluto, there was only empty space. But new data from probes, ground-based telescopes, and James Webb show the opposite. Beyond Neptune exists a dark region that's crowded, chaotic, and full of anomalies, where familiar laws begin to collapse. And it's precisely these anomalies that are whispering, "Our map of the solar system has never been complete." When we begin to suspect that the solar system doesn't have a clear edge, the next question is almost unavoidable. What exactly is this thing we're calling the Kuiper Belt? Not the name in textbooks, not the thin ring neatly drawn around the sun, but the actual physical structure that exists out there, governed by gravity, time, and history. One of the most common misconceptions is imagining the Kuiper Belt as a shell surrounding the solar system, like a bubble. This way of imagining is not only geometrically wrong, but also conceals the dynamical nature of this entire region of space. The Kuiper Belt is not a shell, not a sphere, and certainly not the final wall. It's a thick disk, relatively flat, lying nearly in the same plane as the orbits of the major planets, and extending outward beyond Neptune's orbit. If viewed from above, the Kuiper Belt looks like a giant donut. But if viewed from the side, what appears is not a thin line, but a band of matter with considerable thickness, where orbits begin to tilt slightly, overlap, and phase shift with each other. It's precisely this imperfection that's the first clue showing the Kuiper Belt is not a structure placed there by chance. To understand why, we must turn back time over 5 billion years, when the solar system didn't yet have the familiar shape of today. At that time, the sun had just formed from the collapse of a cloud of interstellar gas and dust. The remaining material didn't disappear, but formed a flat, rotating disk surrounding the young star. In this disk, dust particles collided, accreted, gradually growing into planetary embryos. This is a familiar picture, but what's rarely emphasized is this process was not at all neat. The formation of giant planets like Jupiter, Saturn, Uranus, and Neptune was a violent process at the gravitational level. When a planet reached sufficient mass, it began to clean up the surrounding area, pulling matter into itself or throwing them far away with gravitational kicks. Most of the matter in the region beyond Neptune never had the chance to merge into a large planet. Instead, they became leftover fragments, precisely the precursor of the Kuiper Belt. But if everything stopped there, the Kuiper Belt today would have to be a completely chaotic region, with random orbits and messy distribution. What's noteworthy is, it's not like that. When astronomers began cataloging thousands of Kuiper Belt objects, they realized that many of them lie in orbits with clear structure, especially orbits in resonance with Neptune. The most typical example is Pluto. Although Pluto's orbit crosses Neptune's orbit, these two bodies never collide. The reason is because Pluto lies in 2 resonance with Neptune. For every 3 orbits Pluto makes around the Sun, Neptune completes exactly 2. This is not coincidence. It's the trace of a prolonged process, where Neptune's gravity has captured Pluto and a series of other objects into stable orbital rhythms. Such objects are called resonant Kuiper Belt objects, and their existence shows the Kuiper Belt is not a static structure. It has been shaped, and the main shaper, once again, is Neptune. According to modern dynamical models, especially the Nice model, the giant planets didn't form in exactly their current positions. During the first hundreds of millions of years, They migrated, slowly, but enough to change the entire structure of the solar system. Neptune, in that process, drifted outward, and as it moved, its gravitational field acted like an invisible plow blade, pushing, pulling and rearranging the pile of icy debris ahead. An intuitive visualization is to imagine a large ship slowly moving through water full of duckweed. It doesn't clean up the duckweed, but leaves behind streaks, gaps, and ordered structures. The Kuiper Belt bears precisely such traces. The resonance zones, the object gaps, and the orbital distribution all reflect the migration history of the giant planets. This also helps us understand why the Kuiper Belt is not homogeneous. There are objects in the classical Kuiper Belt with nearly circular, stable orbits, tilted very little relative to the ecliptic plane. These are long-time residents, little disturbed, like orbital fossils. But there are also objects belonging to the scattered disk, with elongated, strongly tilted orbits, signs of having been kicked far away by Neptune in the past. More importantly, the boundary between these groups is not sharp. They transition into each other, like sedimentary layers stacking on top of each other in geology. This once again shows the Kuiper Belt is not an administrative boundary, but a continuous spectrum of gravitational history. An interesting example is when astronomers use data from the OSS survey Outer Solar System Origin Survey. The original goal of OSS was not to search for strange things, but to systematically map the orbital distribution of trans-Neptunian objects, minimizing observational bias. But it was precisely that caution that made the results remarkable. Instead of a simple fading belt, the data showed orbital clusters, gaps, and dynamical grooves that can only be explained by prolonged gravitational interactions. At this point, an old assumption began to shake. If the Kuiper Belt is the outermost edge of the solar system, why does it bear so many structural traces? A true edge, in the physical sense, would be where order collapses, where orbits become random due to lack of shaping agents. But the Kuiper Belt shows the opposite. Subtle order at very great distances. This leads to an important consequence. The Kuiper Belt cannot be understood separately from the rest of the solar system. It's not outside, but an extension of the same dynamical system. What happens near the Sun? What happens with the giant planets? All leave traces here, like ripples frozen in ice. It's also for this reason that the Kuiper Belt becomes an ideal place to test planetary formation models. While the inner planets have been restructured, melted, eroded, and constantly collided, many Kuiper Belt objects have retained a nearly pristine state. They're not just debris, they're records. But a record only has value if we read its language correctly. And the language of the Kuiper Belt is not surface shape, but orbits. Each degree of inclination, each eccentricity, each resonance is a sentence in the gravitational story spanning billions of years. The problem is, when scientists began to read more carefully, they realized that some sentences in this record don't match the rest. There are orbits that cannot be explained by Neptune alone. There are structures appearing at distances where standard models predict matter should have been cleared out long ago. And this is precisely the moment when the Kuiper Belt shifted from a secondary research area to the center of a bigger question. If what we see here is not just remnants, but traces of processes not yet accounted for, then perhaps our solar system is not only larger in size, but also more complex in structure. The Kuiper Belt, after all, is not the answer. It's evidence. Evidence that the history of the solar system hasn't been told completely, and that out there, in the region of space we once considered peripheral, there may exist elements that haven't yet been put on the map. For most of astronomical history, the Kuiper Belt only appeared as faint dots of light. Despite increasingly powerful telescopes, most trans-Neptunian objects were still just blurry pixels, shapeless, without detail. We knew they existed, knew their orbits, but had absolutely no idea what they looked like. That assumption persisted until a small probe, launched from Earth in 2006, flew through space for over a decade, past Pluto, and continued diving deeper into the Kuiper Belt. When New Horizons left Pluto in 2015, many people thought its scientific mission was nearly complete. But it was precisely after that moment that the spacecraft began to conduct one of the most important observations about solar system formation history. New Horizons' next target had the official name 2014 MU-69, a small, dim object lying deep in the classical Kuiper Belt. To the extent that before approach, it only appeared as a dot thousands of times fainter than Pluto. There was no sign it was special, and it was precisely that which made it perfect. On January 1, 2019, New Horizons flew past this object at a distance of just over 3 kilometers. The first images sent back to Earth made the scientific community stop. Instead of a round, icy sphere, what appeared on screen was a strange shape. 2 flat, dark red lobes, stuck together through a narrow neck, like 2 pancakes pressed together. This object was later named Arrokoth. At first glance, Arrokoth looks almost naive. It has no large impact craters, no deep cracks, no signs of violent events. Its surface is suspiciously smooth, and it's precisely that blandness that makes Arrokoth a foundational discovery. For decades, one of the biggest questions in planetary science has been, how do planets actually form? There are 2 main competing scenarios. The first scenario suggests this process is violent. Large rock masses collide, shatter, then merge back together over millions of years in a chaotic environment. The second scenario, less intuitive, suggests the initial formation process happens very gently. Dust particles and small pebbles drift slowly in the protoplanetary disk, gradually accreting through weak gravitational force. The problem is, both scenarios have weaknesses. Violent collisions explain the diversity and chaos in today's solar system, but struggle with the early stage. Collisions at intermediate sizes often tend to destroy rather than build. Meanwhile, the gentle accretion model runs into the meter barrier. At sizes around a meter, objects tend to fall into the sun before they can grow further. Arrokoth, in that sense, is like a natural experiment frozen from a very early moment. Its 2 lobes have different sizes, but shapes nearly intact, not crushed, not broken. The contact point between them is so smooth, it's hard to explain by a high-speed collision. Dynamical analyses show these 2 masses may have drifted around each other for a long time, gradually losing energy, before touching each other at a velocity equivalent only to human walking speed. Such a collision cannot happen in a chaotic environment. It requires a space where relative velocities are extremely low, where particles aren't constantly stirred by large planets. And that can only exist in the outermost region of the protoplanetary disk, precisely where the Kuiper Belt formed. This leads to an important conclusion. The Kuiper Belt doesn't just preserve ancient matter, but also preserves ancient physical conditions. Arrokoth doesn't just tell us what initial matter looked like, it tells us how peaceful the initial environment was. If we look at the inner planets, we no longer see traces of this phase. Earth has melted, differentiated, collided, and restructured hundreds of times. Mars bears marks of ancient oceans, giant volcanoes, and collisions that change the entire surface. Even asteroids in the belt between Mars and Jupiter have been baked hot, smashed and torn apart by Jupiter's gravity. Arrokoth hasn't. It has no atmosphere to erode, no geological activity to remake the surface, no giant planet close enough to disturb its orbit for billions of years. It has nearly maintained its state from the time the solar system first formed. In planetary science, this is extremely rare. The existence of such an object shows the Kuiper Belt has avoided most of the recycling process that other regions in the solar system had to undergo. And it's precisely this that turns the Kuiper Belt into a unique archive. Not an archive of large objects, but an archive of the first stage of planet formation, a stage we can hardly reconstruct from anywhere else. But Arrokoth also shows something more subtle. Its dark red color isn't random. Spectral analysis shows Arrokoth's surface contains complex organic compounds, formed when methane, ammonia, and water ice are bombarded by cosmic radiation over long periods. These compounds, often called tholins, are precursors to prebiotic chemistry. This doesn't mean life exists in the Kuiper Belt, but it reminds us that the chemical building blocks of life don't just form near the sun. They existed, and still exist, in the most distant, coldest regions of the solar system. And if these building blocks are preserved in the Kuiper Belt, it's very likely some of them were transported into the solar system in the past, through comets and orbit-perturbed objects. In that sense, the Kuiper Belt isn't just a repository of planetary formation history, but also a source of chemical raw materials for the inner worlds. The key point here is Arrokoth isn't a strange exception. It represents a large population of classical Kuiper Belt objects little disturbed, maintaining their original structure. But it's precisely when we understand this initial quietness that a new paradox begins to emerge. If the Kuiper Belt was once a gentle environment, where objects drifted slowly and accreted gently, then what happened afterward to create the strongly tilted orbits, the extremely fast rotating objects, and the structures bearing signs of violent collisions? If everything started with quietness, then somewhere in history, energy was pumped into the system. And when we begin to trace those energy signatures, the Kuiper Belt no longer looks like a silent museum. It begins to appear as a place that has undergone violent events, giant collisions, and processes we still don't fully understand. Arrokoth shows us the beginning. But to understand how the Kuiper Belt truly transformed, we need to look at objects that no longer maintain that quietness. Worlds that have been pulled, twisted and bent by the harsh dynamics of the outer solar system. And one of the most extreme examples of that deformation is named Haumea. If Arrokoth represents a pristine, quiet, and almost motionless Kuiper Belt, then there's an unavoidable truth. Not every trans-Neptunian object has maintained that quietness. Some of them bear traces of events so violent they're hard to believe, especially when we remember this region of space is cold, sparse, and very far from the solar system's main energy source. Among such objects, there's one name so prominent it nearly challenges intuition from first glance: Haumea. Haumea was discovered in 2004, nearly simultaneously with Eris. And from the start, it didn't resemble any known dwarf planet. While most large objects in the solar system tend to gradually approach spherical shape due to self-gravity, Haumea is abnormally elongated. Instead of round, it has a shape like a squeezed rugby ball, or an egg stretched along its long axis. This shape isn't an aesthetic detail. In planetary physics, shape is a direct signature of dynamics. The cause lies in rotation speed. A day on Earth lasts 24 hours. A day on Jupiter is only about 10 hours. But Haumea completes one rotation in just under 4 hours. This is the fastest rotation speed ever recorded for a large object in the solar system. At this speed, centrifugal force at the equator nearly directly opposes the gravitational force holding Haumea together. If Haumea rotated just a little faster, it might have been torn apart. In celestial mechanics, there's a limit called spin limit, the maximum rotation speed an object can endure before losing structural stability. Haumea is rotating right at that threshold. This raises a very uncomfortable question. How can an object in the Kuiper Belt have accumulated so much angular momentum? It cannot be the product of gentle accretion like Arrokoth. There's no way a slow, gentle process could create a world spinning frantically like this. The only reasonable way is a giant collision. When scientists began simulating Haumea's history, they realized that its shape, rotation speed, and even its satellite system all point to the same scenario. In the distant past, Haumea was struck by another large object at velocity high enough to transfer enormous angular momentum to it, while simultaneously tearing off a large portion of the outer layer. What's interesting is, the fragments from this collision didn't disappear. Today, Haumea has at least 2 known satellites, and more importantly, it's the center of a collisional family. A group of smaller Kuiper Belt objects with very similar orbits and chemical composition. This is an extremely rare phenomenon in the Kuiper Belt, where object density is so low that large collisions should be nearly impossible events. And that's precisely the problem. The Kuiper Belt, according to all simple models, is a sparse environment. Distances between objects are enormous. The probability of 2 dwarf planet-sized bodies colliding with each other is extremely low. But Haumea exists. Its collisional family exists. And that forces us to accept that the past Kuiper Belt doesn't resemble today's Kuiper Belt. One possibility is the initial matter density in the trans-Neptunian region was much higher than now. This fits planetary formation models. Most initial matter was cleaned out, thrown outward, or fell into the sun during giant planet migration. What remains is only a very small fraction of a once much more crowded structure. If that's true, then Haumea isn't just an individual anomaly. It's a remaining trace of a violent period in outer solar system history, a period when energy was pumped into the Kuiper Belt, deforming, breaking, and rearranging objects there. But Haumea's story doesn't stop there. In 2017, observations using the stellar occultation method brought another surprise. Haumea has a ring system. This immediately made the scientific community frown, because rings are usually associated with giant planets, where gravitational force is strong enough to keep debris particles in stable state. The fact that a small dwarf planet like Haumea has rings raises another question. How were energy and matter from the collision distributed to create this structure? Clearly, it wasn't just one collision, then everything settled down. The Haumea system has evolved, restructured, and retained dynamical traces for billions of years. At this point, a new picture begins to emerge. The Kuiper Belt isn't a place with only one single state. It's not completely quiet like Arrokoth, nor completely chaotic. It's the layered result of multiple phases. Gentle accretion phase, phase disturbed by planetary migration, and high-energy collision phase. What's important is all these phases leave traces, and because the Kuiper Belt isn't wiped clean by heat and restructuring like the inner region, these traces still exist. Haumea shows us that energy doesn't disappear. It's locked into rotational motion, in distorted shape, in satellites and fragile rings. In that sense, Haumea is a momentum reservoir, a physical record documenting an event we no longer have any way to observe directly. But it's precisely here that a deeper paradox begins to emerge. If the Kuiper Belt was once crowded enough to allow giant collisions like that, then why is it today so sparse? It seems nearly empty. Where did the energy come from? And more importantly, where did it go? Where did the objects thrown outward go? What structures did the stretched orbits lead to? And this is when we realize not all traces of energy lie in shape or rotation speed. Some of them lie in much more subtle structures. Structures that, if we don't observe carefully, we'll overlook because we think they shouldn't exist. One such structure, so fragile it should have disappeared long ago, is quietly orbiting another dwarf planet in the Kuiper Belt. A structure that doesn't fit the familiar rules of gravity. And it's precisely here that the story shifts to an object that forces scientists to admit we don't yet fully understand how planetary rings actually work. Its name is Quaoar. After Haumea, one might tentatively accept that the Kuiper Belt has undergone violent events, large collisions, momentum transfer, matter torn apart. All these things, though rare, still fall within the scope of familiar physics models. But there's another type of anomaly, not from violence, not bearing distorted shape, not spinning frantically, yet directly challenging the foundational rules of gravitational mechanics. That anomaly takes a shape so simple it's easily overlooked. A thin ring. In astronomy, planetary rings are a concept that seems very well understood. Saturn has rings. Jupiter, Uranus, and Neptune all have rings. Even some small asteroids and centaurs have been discovered to have rings. But behind that familiarity is a very strict physical principle. Rings can only exist at certain positions. This principle revolves around a concept called Roche limit. Simply put, Roche limit is the minimum distance at which an object can maintain its structure while orbiting a larger body. If a satellite enters inside this limit, the non-uniform gravitational force of the central planet will tear it into debris. Those debris, lacking conditions to reaccrete, will spread into a ring. Conversely, beyond the Roche limit, the story reverses. At that distance, tidal force weakens enough for material fragments to collide and stick together. In theory, if a ring lies beyond the Roche limit, it won't be stable. In just a very short time, on astronomical scale a few tens to few hundreds of years, particles in the ring will accrete into one or more satellites. This is one of the cleanest rules of planetary mechanics. Little gray area, few exceptions, until Quaoar appeared. Quaoar was discovered in 2002, a dwarf planet about half the size of Pluto, lying in the classical Kuiper Belt. For many years, it didn't attract too much attention. Its orbit was quite stable, shape nearly spherical, no signs of obvious geological activity. It was the type of object people would easily categorize as already understood. Until 2023, in a stellar occultation observation campaign, when Quaoar passed in front of a distant star, astronomers noticed anomalous signals in the light curve. Instead of a single light decrease, the familiar signature of an occulting object. The data showed small, symmetrical decreases occurring before and after the main event. The only reasonable interpretation was, there's a thin, ring-like structure orbiting Quaoar. The moment this ring's distance was calculated, the problem immediately emerged. Quaoar's ring lies at a distance 7 times its own radius. In other words, it lies very far beyond Quaoar's Roche limit. According to all current understanding, this ring should not exist. not hard to exist, not rare, but in principle, should not. If the particles in Quaoar's ring behaved like ordinary dust, ice or rock, they should have accreted into a small satellite long ago. The fact they still maintain a thin, stable ring structure over the observation period is a direct challenge to the standard accretion model. The scientific community's initial reaction wasn't panic, but attempting to save the theory. Some hypotheses were proposed. Perhaps particles in the ring have very high elasticity, colliding with each other like rubber balls, causing them to bounce rather than stick. Perhaps there exists an undiscovered small satellite, playing the role of shepherd moon, continuously stirring particles in the ring and preventing them from accreting. These hypotheses aren't unreasonable, but they share one worrying commonality. They're all patching. They don't originate from prediction, but from trying to explain an unexpected observation. And it's precisely that which makes Quaoar important, because it shows that even the seemingly most certain rules of planetary mechanics can have blind spots, especially under conditions we observe least: low density, extremely low temperature, and very far distance from the sun. More importantly, Quaoar isn't the only case. Previously, astronomers had discovered rings around Arrokoth and Haumea, objects much smaller than the giant planets. Each time like that, theory had to loosen a bit more. But with Quaoar, this loosening begins to become significant. At this point, a worrying pattern begins to emerge. The Kuiper Belt doesn't just contain strange objects in terms of shape or collision history. It contains stable structures that current theory cannot predict. And when a stable structure exists where it shouldn't exist, there are two possibilities. Either our physics is incomplete, or there's a dynamical factor we haven't included. That factor doesn't necessarily have to be a new planet immediately. It could be collective interaction between objects. Could be long-term influence of weak but continuous gravity. Could be remaining traces of a structure that once existed in the past and hasn't completely dispersed. But whatever it is, Quaoar is sending a clear message. The Kuiper Belt doesn't follow the simple rules we're used to using for the inner solar system. Here, different timescales, different densities, and different histories combine to create new stable states. States we're only beginning to recognize. This has an important consequence for the main content thread. If even fragile structures like rings can exist beyond prediction in the Kuiper Belt, then larger, more subtle structures, like orbital distributions, tilted clusters, or gaps, may also carry information we haven't read correctly. And as we continue broadening our view, another old assumption begins to shake. The assumption that these distant worlds are all no longer active, that they're too small, too cold, and too far to have any intrinsic activity. Quaoar has shown that even satellite formation rules aren't completely correct here. So, then what else have we underestimated? The answer begins to emerge when modern telescopes, especially James Webb, begin looking deeper into the chemical composition of these seemingly inactive worlds. And among them, there's one name that forces scientists to admit distant doesn't mean lost. For a very long time, planetary science has operated based on an intuition that seemed obvious. The farther from the sun, the simpler everything becomes. Less energy, less movement, fewer surprises. According to that view, worlds beyond Neptune were seen as frozen ice blocks, preserving their shape not because of any sophistication, but because nothing was strong enough to change them. This assumption wasn't entirely baseless. The sun is the solar system's main energy source, and at distances of tens to hundreds of astronomical units, the amount of solar radiation decreases to only a very small fraction. Surface temperature in the Kuiper Belt can drop near the level where molecules almost don't move. Under such conditions, imagining these worlds as ice mummies seemed reasonable. But science often doesn't collapse because of obvious things. It collapses because of small details that refuse to stay quiet. Eris is one such detail. When Eris was discovered in 2005 by Mike Brown's team, initial attention didn't come from its physical nature, but from a classification problem. Eris seemed larger than Pluto, and if Eris was a planet, then Pluto also had to be a planet. If Pluto wasn't, then Eris couldn't be either. That debate led to redefining the concept of planet, and Pluto was demoted to dwarf planet. For a long time after that, Eris was nearly framed in this historical role, the object that dethroned Pluto. But Eris itself lies at a much more extreme position than Pluto. Its orbit takes Eris about 3 times Pluto's average distance from the Sun. At that position, the Sun is just a bright point in the dark sky, not much different from other stars. By all ordinary logic, Eris shouldn't be an interesting world. It's too small to retain initial formation heat for a long time. It's too far to receive energy from the Sun. It doesn't have strong gravitational interaction with nearby giant planets. If there's any object in the Kuiper Belt deserving to be called dead, it's Eris. But when James Webb Space Telescope began observing Eris with infrared spectroscopy, something very inconsistent with this assumption appeared. Eris's surface reflects light extremely strongly. On the albedo scale, Eris is among the solar system's brightest objects, even brighter than fresh snow on Earth. This brightness isn't a side detail. In planetary science, surface reflectivity is a strong indicator of recent history. The older a surface, the more it's been dirtied by cosmic radiation and micrometeorites, the darker it becomes over time. A very bright surface usually means it has been renewed. And that raises an almost unavoidable question. Renewed how data from Webb shows Eris's surface contains large amounts of frozen methane, but not just any methane. Spectral analysis indicates this methane has fresh signatures, meaning it's not simply leftovers from when the solar system first formed. It must have been brought to the surface in relatively recent time on geological scale. Fresh methane cannot naturally appear on the surface of a cold, dead world. It's destroyed by cosmic radiation. It's chemically altered over time. If Eris was just a passive ice block, this methane layer should have darkened and disappeared long ago. The only reasonable explanation is Eris is still active from within. This sounds contradictory, but when examined more closely, it's completely consistent with physics. Eris, though small compared to large planets, is still large enough to retain a rocky core. And in that rocky core, radioactive elements like uranium, thorium, and potassium-40 are still decaying, releasing heat, slowly, weakly, but continuously, over billions of years. This small amount of heat can be enough to partially melt the inner ice layer, forming a subsurface ocean of water ammonia or ice slush. When pressure accumulates, matter from inside can find escape routes to the surface through cracks, erupting gas and liquid, then freezing almost immediately in the deep cold of outer space. This process is called cryovolcanism. Ice volcanism. It doesn't create glowing red lava, but creates bright ice layers, covering the surface, erasing old traces. What's important is, cryovolcanism doesn't need large energy. It needs time. And the Kuiper Belt has plenty of time. Eris, in that sense, isn't a bizarre exception. It's evidence showing trans-Neptunian worlds can maintain intrinsic activity longer than we ever thought. And if Eris can do that at such extreme distance, then closer objects, like Pluto, Make, or even some other large KBOs, are even more likely to not be completely dead. This opens a completely different view of the Kuiper Belt. Instead of a frozen cemetery, it begins to appear as a collection of worlds with their own histories, each world evolving in its own way, influenced by size, composition, and orbit. And here, an important consequence for the main content thread begins to become clear. If objects in the Kuiper Belt aren't just passive remnants, but dynamical systems still operating, then viewing the Kuiper Belt as the outermost edge of the solar system is a dangerous simplification. A true edge no longer interacts, no longer evolves, but the Kuiper Belt is still changing, slowly, subtly, but continuously. Moreover, if these worlds can self-renew their surfaces, then the orbital traces and structures they carry become even more important. Because while surfaces can be renewed, orbits aren't easily erased. Anomalies in motion, in distribution, in spatial arrangement are still there, like impressions of an invisible gravitational hand. Eris shows us that the Kuiper Belt doesn't just preserve the past, but extends the solar system's present very far. But it's also precisely that which makes a bigger question more urgent than ever. If the Kuiper Belt is still active, if objects within it are still interacting, still evolving, then why do we believe its structure has been completely understood? And if that structure isn't complete in our models, then what we're calling the edge may only be the boundary of attention, not a physical boundary. This question becomes particularly uncomfortable when observations begin to show that the Kuiper Belt doesn't end where we once thought, that what's called the Kuiper Cliff, where object numbers seem to collapse, may not be a real cliff, but an observational illusion. And when a probe speeding through that seemingly empty region of space begins sending back data inconsistent with emptiness, the assumption about the solar system's edge is once again shaken. In science, there's a very dangerous moment when data suddenly disappears. Not because the phenomenon ends, but because we no longer see it. Astronomical history is full of such examples. Cliffs in charts are often understood as physical boundaries, until new technology appears and proves they're only boundaries of observational capability. The Kuiper Belt is no exception either. For decades, when astronomers cataloged trans-Neptunian objects, they noticed something that seemed very clear. The number of Kuiper Belt objects gradually increases from Neptune's orbit outward, maintaining high levels up to about 45 to 50 astronomical units. Then suddenly, almost nothing remains. Distribution charts drop straight down, as if someone had cut off the solar system at that point. This phenomenon is called the Kuiper Cliff. The initial interpretation was very simple. The solar system ends there. Beyond 50 AU, there isn't enough matter to form or maintain stable objects. Farther out is just empty space stretching until the Oort cloud, tens of thousands of astronomical units away. A neat ending, an easy boundary to draw. But it's precisely that neatness that's suspicious. Because when scientists examine more carefully, they realize the Kuiper Cliff doesn't resemble a physical boundary. It's not accompanied by any clear mechanism. There's no sudden change in temperature conditions, no phase transition of matter, no known gravitational source that could clean out everything after just a very narrow distance. In other words, the Kuiper Cliff is a conclusion without a clear physical cause. Some scientists began asking more uncomfortable questions. Is the Kuiper Cliff truly a cliff? Or just where our telescopes begin to go blind, To understand why this question matters, we need to remember that Kuiper Belt objects are extremely dark. They reflect very little light. As distance increases, brightness decreases by the square of distance. An object at 80 AU isn't just twice as far as an object at 40 AU. It's 16 times dimmer. And that's before accounting for factors like viewing angle, orbital tilt, or surfaces darkened by radiation. In that context, not detecting objects beyond 50 AU is no longer strong evidence of their absence. It only shows we're hitting observational limits. But doubt remains just doubt, until a completely different data source appeared. When New Horizons left Pluto and continued speeding outward, it carried a small device, less noticed than the famous cameras, a dust counter. This device's mission was very simple: record collisions with dust particles in space. If space beyond the Kuiper Belt was truly empty, dust collision frequency should drop sharply as New Horizons passed the Kuiper Cliff. But that didn't happen. Instead of declining, dust collisions continued to be recorded at levels inconsistent with an empty region of space. This doesn't directly prove there's a larger object population farther out, but it indicates something important. A dust-generating source exists. And dust doesn't appear by itself. It's the product of collisions, erosion, and decay, processes requiring the presence of larger matter. For a time, this data was seen as a difficult-to-explain anomaly, not because it was too shocking, but because no observation tool was powerful enough to confirm. Objects farther out were too dim. Traditional surveys weren't deep enough, and no one wanted to hastily redraw the solar system map based on just a few dust particles. That changed when large telescopes began applying new observation strategies. Instead of sweeping the wide sky and waiting for bright points to appear, some research groups began staring at very small sky regions for long periods, accumulating light bit by bit. This approach requires time, patience, and telescopes large enough to control noise. Subaru Telescope in Hawaii is one such tool. In surveys published in late 2024 and 2025, astronomers using Subaru reported discovering a group of objects beyond the classical Kuiper Belt, lying at distances from 70 to 90 AU. These objects don't lie near the Kuiper Cliff. They lie far beyond it. What's noteworthy isn't just these objects' existence, but how they're distributed. Between the classical Kuiper Belt and the newly discovered population, there's a relative gap, a region of space where very few objects are found. In other words, the structure isn't a fading ring, but more like a ring, a gap, then another ring. This structure isn't at all unfamiliar in astronomy. Debris disks around other stars frequently show multiple rings separated by clear gaps. And, in most thoroughly studied cases, these gaps have a common cause: the presence of planets not yet directly observed. This doesn't mean we've found Planet 9, but it means the Kuiper Cliff isn't a cliff. It's the boundary of a specific ring, not the boundary of the entire solar system. And when looking back with this perspective, many things begin to fit together. Orbits becoming more eccentric and tilted at larger distances. Object density changing discontinuously. Dust still existing where it seemed empty. All suggests that trans-Neptunian structure is complex by layer, not simple by radius. What's worth noting is, we've seen this pattern elsewhere. We just didn't think it applied to our own solar system. Perhaps because we're used to looking at other star systems as complex things, while our own is already understood. The Kuiper Cliff, in that sense, is a lesson in scientific humility. It reminds us that absence of evidence is not evidence of absence. Boundaries we draw often reflect limits of equipment, of observation time, and of initial assumptions. not the true structure of nature. And when this boundary collapses, a deeper question begins to emerge. If the Kuiper Belt doesn't end at 50 AU, if there's at least one more object population farther out, and if between them exists structured gaps, then what is creating that order? A ring can form by itself, but a clear, stable gap, lasting billions of years, usually needs an agent. Something heavy enough to have gravitational impact, stable enough to exist long-term, and far enough to not yet be detected. And it's precisely here that the story begins shifting from our map being incomplete to a harder-to-avoid suspicion. We may be missing a large mass component in the solar system, not as a sensational idea, not as a mysterious planet immediately, but as a logical consequence of what the Kuiper Belt is showing, bit by bit, through shape, through rings, through geological activity, and now through its very spatial structure. To understand that suspicion more clearly, we need to look at objects lying even farther than the newly discovered outer ring. Objects with orbits so strange they no longer belong to the Kuiper Belt in the traditional sense. Objects that seem to belong nowhere at all. And among them, there's one name that has haunted astronomy for over 2 decades: Sedna. In a stable gravitational system, randomness has a very specific shape. When there's no long-term governing agent, orbits will scatter in all possible directions, like ink drops spreading in water. No preference, no special direction, no lasting order. That's why in astronomy, lack of randomness is always more noteworthy than chaos. Detached objects like Sedna, Goblin, and some other distant bodies aren't just puzzling because of distance or eccentricity. What makes them uncomfortable is how they're arranged in space. When their orbits are drawn on the same coordinate system, the long axes don't scatter evenly. They tilt toward the same side. Perihelion points concentrate in a narrow region. Orbital planes also tend to tilt at similar angles. In a system with only the Sun and 8 known planets, such configuration has no reason to exist long-term. Small perturbations accumulating over time will gradually drift all arrangement after hundreds of millions of years, not to mention billions of years. Any directional structure must be blurred. Yet these orbits still maintain their association. To test whether this might just be statistical illusion, research groups conducted Monte Carlo simulations, allowing millions of random orbital configurations to evolve under the influence of known planets. Results repeatedly showed the same thing. The probability of creating arrangements similar to observations from just random perturbations is extremely low. Not zero, but low enough to be hard to view as a satisfactory explanation. Another way to approach the problem is to ask the reverse question. If an additional gravitational source exists, what characteristics must it have to create such configuration? Mass must be large enough to affect objects hundreds of astronomical units away, but not so large as to disorder inter-planet orbits. Its orbit must be far enough to not yet be directly detected, but stable enough to maintain impact over very long time. And its influence must be directional, not violent, pulling slowly, bending, and keeping orbits in a common configuration. When these constraints are put into models, there aren't too many choices left. An object with mass several times Earth, lying at distances of hundreds of astronomical units, on an eccentric orbit tilted relative to the ecliptic plane, can fairly accurately reproduce observed characteristics. Not because this model is beautiful, but because other models can't do the same without creating contradictions elsewhere. What's worth noting is in these simulations, the gravitational agent doesn't need to touch detached objects. It doesn't need collisions. Doesn't need to approach closely. Just existing, with sufficient mass and appropriate orbit, is enough that over billions of years, smaller orbits gradually get twisted, precess, and finally get locked in a common configuration. That's how weak but persistent gravity works. Another subtle point is, this configuration doesn't just appear in detached objects. When the model is extended, the same gravitational agent can also create other characteristics already observed in the Kuiper Belt, including abnormal tilted distribution of some populations, and even the tendency to create dynamical gaps at certain distances. Phenomena previously thought unrelated begin to produce consistent results when placed in the same dynamical framework. This doesn't turn the hypothesis about a large unobserved object into truth. In science, a fitting model doesn't equate to certain existence, but it changes the focus of the question. The issue no longer lies in whether we're imagining too much, but lies in if there's no such agent. How many other discrete assumptions must be accepted to patch up the entire picture? Some alternative scenarios have been proposed. A self-gravitating matter disk far away could create collective influence. A stellar flyby event in the very distant past could leave lasting imprint. Even subtle modifications of gravitational dynamics have been mentioned. But each of these options carries its own problems, often requiring very special initial conditions, or unable to explain the entire observation set simultaneously. The important point is, our bits don't lie. They carry no opinion. They only reflect the history of forces acting on them. And when many different orbits tell the same story in independent ways, ignoring that story becomes increasingly difficult. If the Kuiper Belt is an extension of the solar system, if objects within it are dynamical records spanning billions of years, then these orbital associations are like lines written with gravity. No need to see the author to know someone has written. The presence of an invisible mass in that context isn't a sensational idea. It's a natural consequence when trying to keep the entire picture from self-contradicting. Without it, the Kuiper Belt becomes a collection of exceptions. With it, exceptions begin connecting with each other into a logical structure. And precisely when everything begins fitting together too well, another question appears, much more foundational. If the solar system truly has an additional large component like that, then how wrong has our imagination about size, boundaries, and our position in this system been? That question doesn't need an immediate answer, but it forces us to look back at the entire journey from Pluto through the Kuiper Belt, through rings and gaps, through orbits stretched so far they seem to belong nowhere. Not as a series of discrete anomalies, but as a structure gradually taking shape when enough data is placed side by side. For nearly a decade after Sedna was discovered, its orbit was viewed as an isolated case. One strange object isn't enough to shake the model of the entire solar system. But when the number of similar distant objects began increasing, this view gradually became hard to maintain. In the early 2010 seconds, when deeper surveys like OSO's and Dark Energy Survey began providing accurate orbital data for trans-Neptunian objects, something unexpected appeared in data tables. Extremely eccentric orbits, with perihelion lying beyond Neptune, didn't distribute evenly as predicted. Instead, they tended to point toward the same region of space. In 2014, two scientists, Mike Brown and Konstantin Batygin, began seriously examining this phenomenon. Instead of looking at individual objects separately, they placed all extreme trans-Neptunian objects with semi-major axis above 250 AU, on the same coordinate system. Then, a clear geometric pattern emerged. Their argument of perihelion was locked in a narrow range. Instead of randomly distributing from 0 to 360 degrees, this isn't an aesthetic detail. In dynamics, Argument of perihelion is a very forgetful quantity. Even weak gravitational perturbations from giant planets cause it to precess over time. With models having only 8 planets, these values should have been completely blurred after a few 100 million years. But these objects have existed billions of years. To test whether this phenomenon might just be observational bias, Badigan and Brown used Monte Carlo simulations. They created millions of fake systems, in which orbits were randomly distributed but constrained by the same detection conditions as actual surveys. When letting these systems evolve under gravity of the Sun and known planets, the rate of clustering similar to observations appearing was below 0. Baifinger-Yi. This number doesn't mean clustering is certainly correct, but in science, when random probability drops to 1/10,000th level, the just coincidence explanation begins losing persuasiveness. What makes this phenomenon heavier is clustering doesn't just appear in one quantity. Besides argument of perihelion, these objects also show concentration in orbital inclination. Their orbital planes don't scatter evenly around the ecliptic plane, but tilt at similar angles. When two independent dynamical characteristics both give a non-random result, coincidence probability decreases very quickly. In extended dynamical models, when an additional mass is placed at distances of hundreds of astronomical units, this phenomenon appears naturally. No need to assume special initial conditions. No need to manually adjust data. Initially random orbits, over long time, self-organize into a stable configuration, in which argument of perihelion oscillates around a mean value, while inclination is locked in a narrow band. What's important is this process is slow. It doesn't leave violent traces. No collisions. No strong scattering. Only weak but continuous gravitational precession, accumulating over billions of years. This is precisely the type of influence that a distant, dim, and hardest to detect object would create. A little noticed detail is this same model also explains some other Kuiper Belt characteristics already recorded previously, but without unified explanation, including the existence of abnormally high inclination orbits and the tendency to create dynamically sparse object regions at certain distances. Phenomena previously seen as discrete begin connecting in the same mathematical framework. Not all scientists agree with this interpretation. Some studies argue current sample size is still small, and observational bias hasn't been completely eliminated. These debates are necessary, but even rebuttal studies acknowledge the observed orbital structure is real. The question is only where its cause lies. And at this point, clustering is no longer a feeling. It's not visual impression. It's the result of measuring statistics and simulation, a form of order appearing where simple models predict chaos. When a motion system bears traces of long-term gravitational memory, assuming everything is random becomes increasingly hard to defend. No need to name the agent causing this order to acknowledge the order exists. Just looking at how orbits collectively remember the same direction in space is enough. Clustering, in that sense, doesn't answer what's out there. It only answers something simpler, but more dangerous for current models. The solar system beyond Neptune is missing a component in its gravitational equation. When distant orbits begin exhibiting long-term order, the question no longer lies in whether that order is real, but lies in what type of agent can maintain it without breaking the rest of the solar system. This is a constraint problem, not an imagination problem. All possibilities must simultaneously satisfy many strict conditions. And it's precisely these conditions that have eliminated most initially attractive-sounding solutions. The first constraint relates to mass. To affect objects with semi-major axis hundreds of astronomical units, the gravitational agent must be heavy enough to create perturbations that can accumulate over long time. Dynamical simulations show that if mass is lower than several Earth masses, clustering effect will be weak and unstable. Orbits may be temporarily deflected, but will quickly drift back to scattered state. Conversely, if mass exceeds about 10 Earth masses, gravitational impact begins spreading into the inner region, causing measurable deviations in known planet orbits, which isn't observed. The viable mass range is thus squeezed into a fairly narrow band, often mentioned in the range of 5 to 10 Earth masses. This isn't a number chosen because it's beautiful, but because models outside this band all fail in different ways. A lighter agent isn't enough to maintain order. A heavier agent breaks orders already measured very accurately in the inner part of the system. The second constraint relates to orbit. That agent cannot be nearby. If nearby, it would have been discovered long ago, or at least left clear traces in giant planet motion. At the same time, it also cannot be too far and too scattered, because then gravitational influence would become too weak to maintain clustering. Most fitting models usually place this agent at about 400 to 800 AU, on an orbit significantly eccentric and tilted relative to the ecliptic plane. This configuration isn't arbitrary. A tilted orbit allows creating directional locking effects without simultaneously disturbing orbits near the ecliptic plane. A sufficiently large eccentricity allows that agent to effectively interact with detached objects in part of its orbit, while spending most time very far away, where it's nearly invisible to current surveys. A natural question arises. If such an object exists, why haven't we seen it yet? The answer doesn't lie in one single reason, but in the overlap of many observational disadvantages. At distances of hundreds of astronomical units, even an object with size equivalent to an ice planet will reflect very little light. If its surface is dark, with low albedo, apparent brightness may lie below detection threshold of many wide surveys. Additionally, its apparent motion across the sky will be extremely slow, to the extent that in data taken days or weeks apart, it hardly moves relative to the star background. Modern surveys also don't observe the sky uniformly. There are regions obscured by the galactic plane, where high background star density significantly reduces ability to detect dim and slow objects. Many simulations show that even with existing telescopes, an object satisfying dynamical constraints could easily slip through the net if it lies in these disadvantaged regions. Nevertheless, Planet 9 isn't the only explanation ever proposed. One of the most discussed alternative scenarios is stellar flyby. Another star passed by the solar system when it was young, pulling orbits far out and creating eccentric configuration. This scenario isn't completely ruled out, but it requires a fairly narrow set of conditions. Approach distance, flyby star mass, and timing must be fine-tuned to both create initial clustering and not disperse the structure in billions of years afterward. Simulations show that even if such an event occurred, its effect usually decays over time without an agent maintaining order. Another option is a distant self-gravitating disk, consisting of a large collection of small objects with significant total mass. In theory, such a disk could create collective gravitational moments, affecting detached object orbits. However, to achieve observed clustering level, this disk needs mass equivalent to many Earth masses. Such a structure is hard to reconcile with current observational limits, especially in infrared and millimeter wavelengths, where cold and massive matter usually leaves clear traces. Ideas related to adjusting gravitational dynamics at extremely small accelerations are also sometimes mentioned, but they usually only appear as footnotes. These models, when applied to the solar system, struggle to accurately reproduce inner planet motion, which has already been measured with very high precision. modifying gravity law to explain the outer region, but getting the inner region wrong is a price most of the community isn't willing to pay. When options are placed side by side, no choice is perfect. But there are choices less contradictory. An object with medium mass, far away, on a tilted and eccentric orbit, can simultaneously explain clustering, not break the solar system's inner part, and still fit with not yet being directly observed. This doesn't turn that hypothesis into truth, but it makes it the most economical explanation currently. More importantly, this approach doesn't require believing in an unseen entity. It only asks acknowledging that when dynamical constraints are strictly applied, space for viable explanations becomes very narrow. In that narrow space, Planet 9 emerges not as a mythical character, but as the variable best fitting what's being measured. And that's why, in the current context, Planet 9 exists as a working hypothesis. It's specific enough to test, modest enough to be refuted, and consistent enough to be seriously considered. It's not the final conclusion, and doesn't need to be. Its value lies in it, allowing scientists to ask the right questions, design appropriate surveys, and test whether the solar system out there truly contains an additional component not yet drawn on the map. When inner planets have been measured to millionths, when Mercury's orbit is used to test relativity, it's easy to believe the solar system is a completed structure, a stable system, finished drawing, where what remains is just side details. But the Kuiper Belt doesn't carry the feeling of a detail. It carries the feeling of an uncolored part of the map. In that dark region, objects don't just drift. They record history. Each elongated orbit, each abnormal inclination, each hard-to-explain association is a form of dynamical fossil. Unlike rocks on Earth, eroded and recycled. These orbits almost don't forget. They preserve information about forces that acted on them, not in shape, but in motion. In that sense, the Kuiper Belt isn't a belt of unconscious fragments. It's the solar system's gravitational record, extending from the chaotic initial formation phase to the present. What we read from this record isn't a neat story. It's a story with gaps, with blurred sections, with chapters that have titles but missing content. Planet Neo, whether it exists or not, is just one way to interpret those gaps. It's not the center of the story, and doesn't need to be. The true value of this hypothesis lies in it forcing us to acknowledge that the solar system beyond Neptune isn't a closed part. Something in the picture is missing, and that missing is serious enough to skew models if ignored. This view changes how we understand planetary formation. If the solar system can retain or create large structures at very far distances for such long time, then planetary formation isn't just the story of a few dozen astronomical units around the central star. It can be an extended, layered process, with components only becoming clear after billions of years of dynamical evolution. It also forces us to look back at other star systems. When telescopes observe multi-ring debris disks around distant stars, we often view them as exotic structures, more complex than our own. But perhaps the opposite is true. Perhaps the solar system isn't simpler at all, but only harder to read from inside. The rings, gaps, and abnormal distributions we're discovering beyond Neptune may be nearby versions of structures we're used to seeing at distances of hundreds of light years. Earth's position, in this context, also changes meaning. We don't live near the edge of a complete system, looking out at empty void. We live deep inside a gradually fading structure, where inner parts have stabilized, but outer parts are still preserving traces of forces not yet fully understood. The quietness we perceive isn't a sign of ending. but a sign of very long timescale. The Kuiper Belt reminds us that planetary systems don't end with a clear boundary line. They fade into interstellar space, carrying their own history. What we call the edge is often just where observational capability begins to weaken, not where physics stops. Perhaps one day, a large object will be discovered in that distant darkness, and part of the story will be filled in. It's also possible new data will force us to abandon the current hypothesis and rewrite this chapter in a completely different way. In both cases, what's important isn't the name of the explanation, but the willingness to acknowledge that the current map isn't yet the final map. The solar system isn't a completed structure, sealed and framed. It's a dynamical system still being read, still being interpreted, and in the farthest regions, still holding open questions. And therefore, when looking beyond Neptune, what we truly see isn't emptiness, but the next part of a story we've only begun to understand how to read. We don't stand at the solar system's edge. We stand in the middle of an unfinished story,